Okay, in this video, I want to talk about another case of an exponential growth or decay model that it has some, it's commonly you come across, which is called Newton's law of cooling. And so the basic idea here is that if you remember from our knowledge of entropy, that typically systems of high order, high energy, they tend to low energetic states and low disorder. So you can think of the application of it takes a lot of energy to clean up someone's room. It takes very little energy to make it messy. That's entropy. That's the entropy game. So the Newton's law of cooling kind of uses this to help develop a differential equation to help understand how the temperature changes in a particular object that is now inside some sort of outside medium. So let's say T of t is some temperature of an object. It could be of a person at time t. And let T of m be the temperature of some outside medium. So that could be your cup of coffee has some sort of temperature, and you've now subjected to your outside room temperature that's being held at a constant. And the idea of Newton's law of cooling is that the change in the temperature in time is proportional to the difference between the internal temperature, or the temperature of the object, to the outside medium. And so our differential equation that we get from here is the change in my temperature of my object over time is equal to a constant times T minus Tm. And so if we look at just an analysis of this, if T was greater than Tm, if the coffee was way hotter than the room temperature, then we expect the temperature to cool off, to approach, to deflate down. We expect that d dt should be decreasing. And so if you think about here, if it was hotter than the outside temperature, we expect that dt to be negative. That would mean this term is positive. K, that proportionality constant, must be a negative quantity. Okay, so we're going to put in here that K must be negative. If you take out, say, a soda can from the refrigerator, and now I put it in a room that's held at, say, 75 degrees, we expect that can of soda to warm up. In that case, the can of soda is colder than the outside or the room temperature. This is negative. We get negative times a negative. We expect the temperature of the soda can to increase. And the mathematical model dictates that. Now, if K was really big, bigger than 1, that's what that symbol is, much greater than 1 in absolute value. What does that mean? Let's think about this. That would be changing how fast dt is either how big it's increasing or how much is decreasing. So if K was really big, that would mean the derivative would be very large for small deviations. This is a case where I have poor insulation. Okay, we've all taken a coffee cup and just put it into a big coffee cup, and the coffee cools pretty quickly. But we've also put it into a thermos, and the coffee cup stays warm for a long time. That's because in the regular coffee cup, the open top has no insulation whatsoever, and so it decays to the room temperature very fast from its high energetic state in a high temperature. That means if K was very small, it means we are well insulated. And oftentimes we're trying to measure the degree of which a particular material insulates as something is let out to cool over a given period of time. Okay. Now, what's beautiful, we can solve this differential equation using separation of variables. So I can divide through by this entire expression, and so I have all the capital T's over here and all the little t's over here. There's a 1 here. And now I can integrate. We recognize that's a natural log. We can exponentiate, and then we get our mathematical, our solution, our general solution to our mathematical model of cooling or warming. So the temperature of your object is going to equal to our room temperature plus some exponential growth or decay term. We already said decay is negative, so this term eventually goes to 0 in the limit as t goes to infinity. So we say either exponentially, it warms and it exponentially gets there quick, or it cools on pace, depending on if I'm inflating up the TM, warming the TM, or if I'm deflating the TM, cooling the TM. Okay. Let's look at an example of this. Okay, and this just goes through here. If I have an initial temperature, you can absolutely pin down the C and write down a mathematical model or a solution like this. The room temperature or the temperature of the coffee cup or the temperature of the object is equal to the outside temperature plus the deviation from the outside temperature times how much is exponentially decaying to that outside temperature. So here's an example of how we might find the insulation factor of a particular material. Okay, currently right now the object is 90 degrees and the outside temperature is 100 degrees. So you can think of, I have a coffee cup, it's 90 degrees, it's being subjected to some outside temperature of 100 degrees. I expect in the long term this will approach 100 degrees. But I know after, say, 2 hours, the object is 95 degrees. And this could be 2 minutes or what have you. I haven't given units. Okay. So if you're given initially it's 90, and it's now inside and outside medium 100 degrees, what is it? And I know after, say, 2 minutes that it equals 95 degrees. How well is it insulated? What is the value of K? Well, I use my Newton's law of cooling model. I plug in the information. I know that the outside temperature is 100. I know my inside temperature is 90, or my object temperature initially is 90. I have outside is 100, so I have the model is 100 plus 90 minus 100 times e to the kt. I know at t of 2 it equals 95. So I have 100 minus 10 e to the 2k, and I can solve for k itself. So dividing through by 10, taking the natural log, this is using a little natural log rule, and we get that k is minus 1/2 natural log of 2. This is a common technique to be able to find how well an object is insulated. You give me how well it's insulated right now, or sorry, what the temperature is right now. You measure the temperature of the object or the core temperature in a little bit later time. If I know what the constant temperature of the medium that it's in, then I can absolutely estimate the degree at which it's insulated. And this will help you in doing some of your homework problems on the Newton's law of cooling.